Okay, so let's get started. This is the third and the final module of our course. And our course is basically stochastic processes and signal modeling. So let's remind ourselves on the topic of, let me write this, signal modeling. So I would like to first briefly discuss deterministic modeling. And then I will start discussing our topic, which is stochastic modeling. Actually, you have already seen stochastic modeling, for example, Poisson processes, I don't know, Markov chains, etc., that Elif Hoca has started in module number 2, are examples of stochastic modeling. But to understand it, let me again revisit very fastly what is deterministic modeling. So this will be just a revisiting something that you know from many other earlier courses. And I would like to put this deterministic modeling in contrast with stochastic modeling. For example, let me give you an example over here. Let's say that there is a, let me see, I place on top of a table, let's say, a cannonball or a cannon. This is shooting cannonballs, in Turkish top mermisi, okay, to a range. Now, the issue is you would like to find the time that this cannonball hits the ground, okay? So this is a problem, if you think about it, it's like a deterministic physics problem, isn't it? So if this has an initial velocity of this much and this much, so this is, let's say, y component, this is the x component. If I have velocity y, velocity x at time 0, okay, at this point, now the question is, how can I find the impact time? Let's say this is the impact time. Do you remember these problems from physics courses? These are very easy problems. So what is the model? Now you say that at any time, there is something called free body diagram, etc. And you calculate the following kind of equation. Net force on this cannonball is equal to m times, let's say, this acceleration vector. So what is this acceleration vector? M times second derivative of, let's say, position vector. Okay? Actually, this is 3 equations. Acceleration x, acceleration y, acceleration z is equated to the second derivatives and so on. Okay? So in this very simple component, what do we know? So the only net forces in this y direction, according to this. So we have a model like that. This is what we know from physics. This is a deterministic model. So given this initial condition at time 0, I should be able to find the solution over here about the impact time. Okay? This is called the deterministic modeling, and this is what you do. In 105 physics, 106 physics, in circuit theory, given the initial conditions, you find the location of the, not the ball, voltage or the current at a later time. Okay? This is what we call modeling. In control theory, if you are taking 302, now you are changing the velocity by, let's say, you are putting some thrusters over here. This becomes a rocket. Okay? If you put a rocket on this, somehow, this flying object, now you can include an input to this. Now, in this model, you have physics, and also you have the change of adjusting the thrusters of the rocket. So this becomes a control problem, and you want to reach this location as soon as possible, then what do you do? Okay? This is the classical scientific problem. So we have a deterministic model, which is totally constructed through the physical considerations, like induction motor, those kinds of things. And there are some, let's say, initial unknowns, etc., or inputs, and we try to find what will happen later on. So, for example, let's go ahead. In this cannonball example, let's assume that we are only, for simplicity, interested in the height at time, let's say t. Okay? Height at time t. So what is your guess? So at t is equal to 0, it is at this height. Okay. At t is equal to 0, it's at this height. So this is y of t. It's a function of t. Then it will be, what kind of curve will be this? Do you think it will be an exponential curve? Parabol. It's a second order, isn't it? This should be a second order. The reason is, now this is a constant. Why it's constant? Because net force is just the gravity. Gravity is constant. Now you see that this is like a second order differential equation. It's only in one dimension, y dimension. So this is the second derivative is equal to a constant. Okay? Second derivative of a height, rate of change of height, differentiated, second derivative, is equal to a constant. So what do we expect? It will reach a maximum and then it will go over here. Am I right? It will be something like that. So the question is, let's say that I have observed this. Now this becomes like maybe a military problem. So you're observing this from the other end of a, let's say campaign, and you're observing a cannonball at this height 1, at t1, cannonball at height 2, cannonball at height 3. Okay? Now the question is, maybe you're interested in the peak location, maybe you're interested in the, the impact time, etc. Okay? So I should be able to understand this trajectory. So you have said that this is quadratic, am I right? Y of t is equal to at square bt plus c. So in order to find this, why this is quadratic? Because of this, deterministic modeling. So I should be able to find a, b, c, to find any other location. Okay? So do you understand this? So these are my observations. So from these three observations, I should be able to solve a, b, c. Am I right? Can I do this? Yes. I should be able to do this because very simple. Do you agree? At time t is equal to t1, height is equal to, I have measured this. According to physics, it should be equal to this. Then, one equation. So if I write three equations like this, similarly, do you agree? So I can find ABC from here. So let me write for another one just for the sake of completeness. So I'm evaluating this function at t2 and equating to my observation h2, height at number 2. So from here, obviously, I can get ABC. Okay. So physics, mathematics, equation solving, linear equation solving, we are done. If I can find ABC, that is the end of the problem. But let me write a formula. Now, how about this? If I write something like this, would you agree with this? Let me see my notes. Okay. So now I claim that this is the answer. Do you think this is the answer? So this is y of t. I claim that this is this curve. So I'm using another piece of mathematics. So what is that piece of mathematics? Let's see. If there is a solution, then this solution should be a unique solution, isn't it? Let's insert t is equal to t1 over here. Then what do I have? This is 0. This is 0. T is equal to t1, this is 1, height is equal to h1. Very happy. It should be supposed to be like that. When t is equal to t2, this is 0, this is 0, this is equal to, height is equal to h2. Okay? This is called Lagrange interpolator. So as you see, now we have more mathematics. Linear equation, even I don't need to solve this linear equation system. I'm using more and more mathematics, and I can write this after this kind of modeling almost like instantaneously. Do you agree with this with this solution. So this is again a quadratic. You see t squares over here. Okay? There are some constants over here. So I can find a, b, c if you wish by just expanding these multiplications and summing them up if I wish. Okay? So that is it. So what is interesting is that now I have physics, mathematics, and the final result. Now if I tell you that now in my measurements I have some uncertainty. What do I mean by uncertainty? Maybe my radar system is measuring this, so I'm not sure, but somebody tells me that it is in this range. For example, I always make an error, at most an error of delta h over 2. Okay. When I say something, that means that this is not exactly correct, but there is some error over here. Now what can you say about that? Well, this is a different problem right now. This time your observations are somehow random. Do you agree? Your observations are random. So height is random, height is random. Maybe you know only the mean value of this random variable. Then you try to do something with that. That becomes stochastic modeling. Okay? We will be studying that. Actually, you have started seeing this. So that will be our goal. So let me give you just one more example and then we are done. So this would be second example. Okay. So let's assume that x of t is band-limited signal. Okay. And let's say that x of n is, since these are very familiar to us in electrical engineering, sampled version of it. So let me have something for the band-limited signal. So this is my x of t. And let me have the samples like this. This is 0th, first, second, minus first, so on. So this is x of n, but I should write then ts over here. Okay? Because this is equal to, sampled version of the continuous time signal. Now the question is, if I only know the samples, can I reconstruct another, value of this in between samples of this function? Can I reconstruct it? I should be able to reconstruct. This is called sampling theorem, isn't it? If this is band limited, if I sample it fast enough, I should be able to reconstruct this. Don't you think so? Again, there is a formula. Let me write this. X of ts, these are my samples. Let me think. Okay. So this is my band-limited interpolation, again interpolation formula. And this is the basis of signal processing, because we would like to always process continuous time signals, isn't it? This is life. By just, digitally, reliably. So band-limited interpolation. This is our sampling theorem. So we are assuming that fs, sampling rate, things like that. You can refresh your memory. Sampling rate, 1 over ts, sampling period, is greater than equal to 2 times f max. Let's say greater than, just to be sure. Okay. F max is the maximum frequency of band-limited signal. Things like that. Okay. I don't want to give these details because this is not our topic. This is topic of some other course, 301. Okay. Or 430. There are other courses for that. But what is interesting right now is that, given these observations, but how many observations do I need? Infinite. So I am able to evaluate another sample value of this function, let's say at this point. Okay. So let's say that this is point t is equal to tx. Then when t is equal to tx, I put tx over here essentially. I know these samples, I linearly combine them, and I get my result at t is equal to tx. Similarly for this one, very similar. When I evaluate it at a time, here are my samples. I calculate them by adjusting some weights, and I get my result. Okay? Both of them are linear operations. This is signal processing, basic signal processing, and this is what we do. Again, what do we have? We have a physical fact, band-limited signal. We have mathematics behind it, and we get, let's say this is the output sample, by processing observations. Okay? So you see that this is totally deterministic. Everything is fixed. In 90% of the courses that you have taken, always the subject is like that. But what happens if you have some, as I have said, randomness? Okay? Now that will be the topic of stochastic modeling or random processes. Okay, so we are continuing from this point. So this is also called random processes is equivalent to stochastic processes. So both of them are equivalent. And I would like to define a function which is constructed with a free variable and outcome from a sample space. So sample space is related with a random experiment. Is called a random process. This is somewhat abstract. So what do I mean by this? X is a, this is tau, x, t, and tau. So tau is outcome of a random from a sample space. T is the variable of the function. Okay? So you can say that tau is an element of sample space, something like this S. And T is this. T is like a variable. This is called our random process. For example, Elif Hoca was discussing counting processes, isn't it? There is a T and there is a random element. That random element is the arrival times, for example. At every arrival time, you increment the value of the function by 1, something like that. Okay? So let's try to look at this with an easier example, and let's try to understand how can I model such things. So let's have a simple example to illustrate the random processes. So this is RP is random processes. So let me have this example, and I will call this example as random slope signal. You will see why. Now I'm assuming that x tau of t is, this is a times t, okay? And a is, let's say, uniformly distributed in 0, 1. Okay. So this looks something simple. It's a function of time. And there is only one parameter, a. But only thing that is maybe different is that a parameter is selected from a distribution, sample space. Okay? So let me illustrate this. This picture will be important. So this sample space, you may think about it like you have a bag. In your bag, you have all numbers in between 0 and 1. This is a strange kind of bag, all real numbers in 0 and 1. And then, by nature or someone gives you A, and then you have, for example, something like this. So let me say that this is tau 1, and then this is x. Let me put tau 1 over here. Tau 1 is, let's say, 3. It cannot be 3. Let's say 4 over 5 t. Meaning that the slope is 4 over 5, and so on. So what is this tau 1? Tau 1 is actually a selection for this A, random variable A. So sample spaces, in this case, this is related with this. All numbers in between 0 and 1 are in the sample space. Outcomes, they are the outcomes of this experiment. So you are selecting just one outcome. Okay, outcome. And then you are starting this function. So let me have one more outcome. Let me have another one. Let's have 3 outcomes. So this is tau 2. Let's say that this is 1 over 2 slope. This is tau 3. So it generates 1 over 3. Okay? A slope like that. So this is my third function. So do you think this is totally random? It's not totally random because you see that the slope is in between 0 and 1. For example, my highest slope function is somewhere, this is let's say 1, is over here. And the lowest slope is over here. So my functions are always lying in this part. Do you agree? Because this is the highest possible slope, this is the lowest possible slope. This is not totally random. People think that most students or someone who is not with enough experience, they think that random means unpredictable. It's not unpredictable. I can say that there won't be any points over here, over there, etc. Okay, there is some information over there. So again, my goal can be, maybe I'm observing just, a time value of this experiment. Let's say time is equal to t1. Maybe I'll be observing another time value of this experiment, t2. Okay? Please remember our deterministic experiments. Now I want to say something about t3. So how can I do that? If this is deterministic, like in the Cannonball example, sampling theorem example, we have formulas for that. Now this is random. So how can I characterize this first of all? How can I understand this problem? And then how can I model this, isn't it? This will be our topic. Okay, so please keep in mind this picture. So let me write a note. X tau k of t is called a realization. So this is a terminology, this is R, of random process x of t. Since this is random, I should write it with capital letters. Let me have it like this if you wish. X tau k of t is a realization of random process. This when outcome of the experiment let me write like this. Outcome of experiment, that is the random factor, is fixed. So each one of them are called a realization. Okay? So you may say this is our essentially third realization. Okay? So in this realization, somehow nature selects, let's say, this slope. Slope turns out to be 3. Okay? Something like that. Now, given these realizations that we face, so what can I do? That will be our goal. So our initial goal is description of random processes. So let me have our first model, joint probability density description. So let me see. So let me have, let's say I, first order p.d.f description. First order p.d.f. So this is the reason that you have studied p.d.fs and other topics. Now let's try to make use of that. First order p.d.f. Let the process be sampled at t is equal to t1. Okay. Then I have the following. X of t, x of t1 is equal to, let me write it for simplicity, x1. For example, t1 is over here. Let's say t1 is equal to, for simplicity, 3. At the third second, I sample this, t1 is equal to 3. And this becomes, what do you think? Is this a random variable, random process? Or is it just a scalar? Is it a vector? What is the x1? What kind of a mathematical object is x1? X of t, this is a function, but this is just evaluation of the function at a specific time. But please be careful that I haven't given you any information about the realization or the outcome of this experiment. So this is just a random variable, okay? This is right now a random variable. So if I evaluate this, you can say that maybe I will observe this, maybe I will observe that, maybe I will observe this. And you can say that they're equally likely somehow, because they're all coming from uniform distribution. It should be somehow reflect that, okay? So this is random variable. So, okay, we will make more definitions like that later on. So our goal is finding the density of x1. That is it. Okay, finding the probability density function. This will be the first order density function. Later on, we will be having two samples, and we will be finding the joint distribution of those two samples later on. But this is the start. So let me write it one more time. x1 is this. And the issue is, I would like to find the density of this x1. So this is the p.d.f, probability density function. It is clear, probability density function. Okay, so in this very simple random slope example, so if I evaluate this at this random process x of t, x of t1, so what do I get? I get this capital A times t1, where A is, sometimes this is older notation. I use tildes, underbar, at the bottom of this label. So also this is denoting that this is a random quantity. Capital letters also denote random variables, but sometimes for additional emphasis, I am putting these tildes on purpose to show that this is the random quantity. T1 is, just the variable of this function. Okay, this is the random quantity, and this is the variable of this function. So what do I know? So I know also the following. A is uniformly distributed in between 0 and 1. So do you remember such problems? If A is uniformly distributed in 0 and 1, let's say that T1 is equal to 3. What is the distribution of 3A? 3 times A. Do you remember such things? Okay, this is called one function of one random variable. So I will be finding distributions. So I will be deriving distributions from some other distributions. So finding, let's say f x of t1, x1 is simply an exercise in one function of one random variable mapping. Okay, so let's do this. If I have x1 is equal to a times t1, okay, and a is equal to uniform 0, 1, how can I find the density of x1? Okay, t1 is a positive quantity, let's say. Okay, so what do you think is the density? If in your mind you can fix a value for t1. If t1 is equal to 3, so I think that if t1 is equal to 3, then x1 is, so think about the experiment. You are picking a random number from the back. Okay, think about a random number. Multiply it by 3, okay, you get a new random quantity. So what will be the distribution of x1 in this experiment? So you can say that this would be again uniformly distributed, this time in between 0 and t1. Because, you know, if it is, my pick is 0. Why it is uniformly distributed? Well, we have actually one function of one random variable discussions. Okay? So I can easily prove this, but please look it up if you need. So we write it like this. F of A, so this is the distribution of A. Let me sketch this. So this is the uniform density in between 0 and 1. And this one is now uniform density in between 0 and t1. Okay? So I should be writing something like this in my opinion. So if I sketch this, f of, I can also write here x1 because this is random variable x1 as I have said. So this will be uniformly distributed, and it is this. This part is something like dotted. This is 0, non-zero, 0, and so on. So this is, for example, if t1 is equal to 3, I have expansion of this up to 3, and I multiply it by 1 over 3. So you get this. Okay, so what do we see? Now we see that f of, or let me write conclusion, x of t1 is again uniformly distributed in 0 and t1. That is something nice, okay? So I have some idea about this random signal. At any time sample, it is uniformly distributed in between 0 and t1 for this random slope signal. Okay, good. So if I have a, let's say, sketch, but maybe I can use that later on. So if I sketch something like this, let me think. Again, let's have the sample space. So this is slope 1. This would be slope 0. And everything is in between. Okay. Now, what do I see? So let me, at t1, I see that this is also equal to t1. At t1, this one maybe, I see all possible numbers in between 0 and T1, uniform distribution, 0 and T1. So if it can be a little bit confusing, but let me try to sketch the following. I see a distribution like that. So in the third dimension, let me have this third dimension like this. Let's erase this. Okay. So I'm sketching this distribution on the third dimension. Maybe I should draw it like going out like this. Okay. So this height is the distribution's value. Uniform distribution over there. Do you understand? So at this moment, I see, the highest value that I see is corresponding to the realization with the maximum slope. It's at this point. So there are several other realizations, like this, and so on. So they are, somewhere over here. And the distribution of the probability density function is, let me write 1 over T1. This is this height, like that. So as time progresses, at t is equal to T2. What do you see? Now the uncertainty increases because the spread of this increases. Am I right? So this height above this plane is 1 over T2. And again, I have this. So another realization, another time instant at T3, I have this. Do you understand what is going on? So most of these discussions are very simple. Only thing that we do is, assume that it's like an exam, you only calculate this trivial thing. But behind this trivial thing, there are lots of drawings, and you should understand what is going on, these kind of pictures. So what do I mean by when I evaluate this random process at a time? When I evaluate this random process at a time, I pick a number from this distribution. When I evaluate it at another time, I pick a number from another distribution. Because as you see, as time changes, T1 changes, let's say, this random variable changes, and so on. Okay, so the first order p.d.f description should be given for all t. For all t. Let me put a comma. That is, we should be finding x t1, x1 for all. Let me write t1 for all t1. Okay. For all sampling instances. So can I do this? Of course. Well, actually, I have just did it for a generic value of t1. It's something like that. This is the end of random slope example. Is this clear, what we are trying to do? Now, after this, we will be going one more step ahead. But maybe before that, let me ask you, okay, here's a question. Well, what is the p.d.f of x of 0? Can you say, what is this p.d.f? X of 0. Exactly. This is the impulse at the origin, because you see at x of 0, whatever this random quantity is, you multiply it by 0. Okay? Or from this sketch, all realizations are passing through 0, all of them. Or from this p.d.f, you move it to over here. So does it look like an impulse? Area is equal to 1. Area is equal to 1, and you just move it. It becomes a tiny pulse, and eventually at the limit it will be an impulse. So let me write it like this. X of 0, let me write it x0 to just mention it. So this is delta of small x0. So if I sketch this, this would be, impulse of weight 1 at x0. Maybe this is too late for these discussions, but please pay attention to this capital letter, small letter. This axis is in small letters because this is the outcome of this essential experiment x0. Okay? So x0 cannot take any value other than 0. This is 0. Okay, this is in brackets 1, means this is the weight of the impulse Do not think that this is the amplitude, this is the weight. You never draw impulses, larger impulses, because impulse is already infinite. Okay? This is the area under the impulse, essentially. Things like that. Okay. Now, let's go ahead. Now let's do, this was first order p.d.f, am I right? Please check this, first order. Now let's do second order. This is joint p.d.f description. Now I think you get the idea. Now I have two evaluations times. And of course, I'm assuming that they are different times. I mean, okay. So the issue is the density of, let me write it like this, x1, x2, small x1, small x2 is the question mark. But as we have said, I want to also find this for all t1, t2 pairs, for all times. Okay, this idea, but right now I have two evaluation times, maybe t1 and t2. Okay, that is it. So this will be called second order p.d.f description. And later on we will describe, for example, Poisson process and some other processes also using this kind of modeling. Okay, this is very general, as you see. We can do lots of things with this kind of a model. So second order p.d.f description is this. Now the issue is, let's go back. Again, study this, random slope signal. So how can I find this for the random slope signal? Okay, let's give it a try. Now my x1 is a times t1, this is the random quantity. My x2 is a times t2, this is my second observation. So, and I want to find distribution of, let me write it like this. If you consider this is like a vector. Okay, pair. Now I want to, I can write them as a vector, like in brackets, like this, or with commas, etc. I want to find the p.d.f of this. Is question mark. Okay. So let me see. What kind of mapping is this? When I was a student, we were using an old textbook, Papulus's textbook, and this mapping was called, maybe you will remember when I say it. So this is called two function of one random variable. Do you remember this? This kind of a sentence. Two function of a one random variable. Because you have two functions, but there's only one random variable. Okay? Exactly something like that. You have also two functions of two random variables. For that one you calculate the Jacobians, things like that. Okay. This is actually a little bit easier, two function of one random variable, but this is another exercise in probability textbook then. Okay. So the only thing that may be puzzling you is there is so much terminology. Random variable, random process, random variable, deterministic, deterministic. Do you see what I mean? So if I give you, for example, numerical values for these, this will be a much simpler example for you. Again, the notation-wise, it's a little bit complicated. Now I should write this like, this is my first random variable, okay, with tilde, I'm mentioning it one more time. This is my second random variable. And these are the outcome-related variables, x1, x2, density variables, okay? So density variables are, if I want to sketch this, I am sketching them with respect to these x1 and x2 small variables. Okay. That is it. So I should be able to find this. So how can we do this? But before doing that, let's think about it. For example, well, I need the joint distribution of, let me have Let me move this. Let me have this T2. Let me move this T1 over here. Doesn't matter. Now I evaluate this density. No, sorry, this random process at this time, at t is equal to T1, at this time, and t is equal to T2 at this time. So I need a joint distribution of these. So do you understand what I mean by that? For example, do you think this vector, let's say, the first element is corresponding to the observation at T1, second element is corresponding to observation at T2. Can I have 5, 0 over here as 5, 0 vector for this? Well, I cannot have 5, 0 unless this is let's say that T1 is equal to, let's say this is equal to 1 for simplicity. This is equal to 2. So you see that the first element is always in between 0 and 1. The second element of that vector is in between 0 and 2. So you cannot have first element as 5, obviously. Now I have to characterize this vector somehow. So how can I do that? Well, we will be using something very simple. But that will be our goal. Previously, we were only characterizing only one of them. Okay? At this one, if sampling time is equal to also 1, then it's also uniformly distributed in 0, 1. But 1 and 2, joint distribution of that. Okay? So how can I do that? Now, let me write it. Would you agree that I can do this? This is called what? Do you agree that I can do this one? Do you remember this? Maybe you have forgotten it. Then I will just calling Ahmet Hoca. Ahmet Hoca will be, I don't know, won't be happy at least, isn't it? This is called conditional probability, right-hand side. And this is the factorization of this joint PDF in terms of the marginal PDF and the conditional PDF. Okay. You should know this terminology, marginal, conditional, joint, etc. all also, because this is our language. Okay. So, how about this? Have we studied this? I think we have studied this one. You know, I have erased it, but this is done. This is the first order PDF description. Okay. If you wish, if you don't remember it, let me write xt1 over here, just to refresh your memory. Okay? For any sampling time, this is just the marginal of this second order density. I have already done this before, a few seconds ago. So this is uniformly distributed in 0 and T1. So only thing that I need to calculate is this one. This is the question mark. So if I can calculate that, I'm done. Okay, so we will do that calculation after 10 minutes of break. And that's all for this first hour.